We're going to look at the Doppler effect for light, but we're going to introduce the consequences of relativity here. Now, we've already talked about the Doppler effect with regard to sound. With sound, we know that when a source is moving away from us, we see a longer wavelength, or I should say we hear a lower frequency. That's because as a source is moving away from us, the waves, the wave fronts, are having to cover a larger and larger distance, and thus we interact with them less often. Likewise, if we're moving away from the source, the same effect happens. The wave fronts have to cover more and more distance as we move farther and farther away from the source. Now, if we move toward the source, or the source moves toward us, we will experience a higher frequency. That means shorter wavelength. Remember, the speed of a wave is equal to the wavelength times the frequency. So in this case, as we're moving closer and closer, the wavefronts are having to travel a shorter distance. Likewise with the source. If the source is moving toward us, the wavefronts are passing us more frequently. That means a higher frequency and a shorter wavelength. We're going to see the same thing for light, but we have to take into account the fact that if the source is moving fast enough with respect to the observer, we're also going to experience things like time dilation. Okay, let's take a look at this. So first of all, we again think about a source as it's moving through space. As the wave fronts in another frame of reference tend to bunch up in front, we experience what's called a Blueshift. And the name Blueshift basically comes from the fact that in the visible spectrum, blue tends to be a shorter wavelength of light. Doesn't mean that the light's going to be bluer. It means that the tendency is we're going to shift to a higher frequency or a shorter wavelength. Of course, the opposite is true for the redshift. In an observer's frame of reference, if a source is moving away from the observer, then the wavefronts tend to stretch out and we get shifts to lower frequencies, that is, longer wavelengths. Okay, so here's what we have. We have our source, which is moving away from us at some velocity v, and as it does so, in our frame of reference, as it's giving off these light waves actually stretch. Think about it this way. If the observer originally gives off, I should say the source originally gives off the front of these waves at this position right here in this gray reference coordinates, sometime t later, where these white coordinates are shown, the back end of the wave might be emitted. And what happens here, this movement backwards actually allows the wave fronts to stretch out. So that's the same sort of effect that we would expect to see from a source moving away from an observer for sound. Okay, so what do we see here? Well, again, in the observer's frame of reference, the source wavelength, and again, we haven't taken into account any relativistic effects. We're not looking at relativity yet, but the observer will see that the wavefronts have traveled some distance ct, and from the beginning of the wavefronts being emitted to the end of the time, they have stretched out an additional distance vt. So again, in the frame of reference of the source, these wavefronts would have moved some distance ct. In the frame of reference, without considering relativistic effects of the observer, it would be ct plus the distance that the source has moved. So right off the bat, if we want to go through sort of the classic Doppler shift, here's what the wavelength would look like. And again, the wavelength, okay, is the distance between the wave fronts. The frequency is inversely proportional to the wavelength. Remember, the speed of a wave is equal to the wavelength times the frequency. So frequency and wavelength are inverse. The wavelength gets longer, the frequency gets lower. Okay, but that's not everything that's going on here. We also have to take into account that as the source is moving away from us, it is also experiencing relativistic effects. In our frame of reference, time is running slower for that source. So in our frame of reference, if, for instance, the source is giving off, I don't know, waves at 10 to the 14 hertz. Well, the Doppler shift, okay, due to the time dilation, okay, that Doppler shift due to the time dilation is effectively going to mean that we are going to see the oscillations take place over a longer period of time. Period is equal to 1 over the frequency. And as the period gets longer, the frequency gets lower or less, and the wavelengths also get longer. Again, you think about the wavelengths as being equal to the speed of light divided by the frequency. Frequency is inversely proportional to the time. Time is experiencing this relativistic time dilation. This is gamma right here. Gamma is always greater than 1. So T is always larger than in the other frame of reference. So the wavelength also gets larger. So if we take into account those two examples, we take into account those two effects, both the stretching out of the waves, because in a sense, the source is moving away from us, and therefore the distance that the waves have to travel is becoming greater and greater. But also this time dilation effect is going to make the wave fronts spread out, and it's going to make the wavelengths longer and longer. Okay, now notice here, by the way, folks, instead of using nu, I've replaced it with frequency. Nu just looks too much like velocity, but we've used nu in the past, so don't be alarmed if I go back to F and told you at the beginning of the course I was going to just use nu for frequency. Okay, so we put these two effects together. Now we're going to do a little simplification because this is a rather ugly way to write an equation. We want to basically combine the top and the bottom. I can multiply the bottom by its conjugate. That is going to simplify things just a little bit. And basically, when I do that, the square root down here is the square root of this, okay? This 1 plus v over c, square root, is actually the square root of this right here. So anything divided by the square root becomes its square root. And then we see this right here. And finally, our wavelength for our observer is going to be equal to the wavelength that the source gives off in its frame of reference times the square root of 1 plus v over c divided by 1 minus v over c, okay? Again, I got to be a little bit careful here how I said this. I didn't multiply it by its conjugate. What I did is I actually factored this out into 1 minus v over c times its conjugate. So I apologize for that. So in any case, what we're doing is we're taking a shorter wavelength, and basically for something moving away from us, as we would expect, the wavelength becomes longer, but the wavelength becomes longer than it would in terms of just classical physics, okay? And again, it's two things. It's that classic Doppler shift that we would expect for a source moving away from an observer, but it's also the time dilation. So we call this the parallel Doppler shift. Parallel, what is parallel? Sometimes it's known as a longitudinal. It is when the light is traveling parallel to the direction that the source is moving, okay? And again, our wavelength becomes longer in this particular case. For a source moving away from us, the frequency becomes lower. You get the opposite effect for an object moving toward us. Basically, if it's moving toward us, then we're reversing the signs for V, and we get a shorter wavelength. We call this blue shifted, and we get a higher frequency, okay? Now, let's do some applications here. One of the most important applications for the Doppler shift is, of course, measuring the redshift for the expansion of the universe, looking at galaxies and looking how the spectral lines will change as a function of distance, which is really a function of velocity. Now, if we go to cosmology, we do understand that the universe is expanding, which means that the further away something is from us, the faster it's moving away from us, because if the universe is expanding, points that are further from us are having higher and higher velocities from us. It's called the raisin bread analogy. And basically, if you make raisin bread, you put raisins in the dough rises, it expands to occupy more volume as the yeast generates carbon dioxide. And as the volume of the bread becomes larger and larger, the space between the raisins becomes greater. Raisins with greater distance experience the greatest amount of velocity. So that's a little more cosmology than you would have liked. But let's take a look at an example of two galaxies. One is moving away from us at half the speed of light, and the other one is moving toward us at half the speed of light. What is going to happen to the wavelength of the light that is given off by each? Now, let me just tell you, first of all, that having a galaxy move away from us at half the speed of light is a very realistic situation. If we're looking at very, very distant galaxies, we do see these galaxies moving at very, very large recessional velocities. What's not so realistic is to have a galaxy moving toward us at half the speed of light. That sort of contradicts the idea that the universe is expanding. We do have galaxies moving toward us. Andromeda is moving toward us, but not at such a large, nearly luminal speed. Okay, so let's just do our hypothetical here. We take 1 plus half the speed of light. We get 1.5 divided by 0.5. That's the square root of 3. The square root of 3 is roughly 1.7. So whatever I see from that galaxy, the spectral lines are going to be shifted by a factor of 1.7. Okay? 1.7 in terms of the wavelength. In terms of the frequency will be reduced by a factor of 1.7, or we would say that the source frequency divided by 1.7 would be equal to the observer frequency. Okay. Now, for the galaxy moving toward us, this is a blue-shifted galaxy. This would be very, very unusual. And at half the speed of light, I'm really not aware that we have any such galaxies. But in this case, we take 1 minus 1/2, that gives us 1/2, divide that by 1.5, we get 0.6 times the original source wavelength. We would get a blue shift. So for instance, if light were given off at 500 nanometers, that's basically in the middle of the visible spectrum, that's green, it would be shifted all the way to 300 nanometers, which is the near ultraviolet. Now, in real applications, one thing that we like to look at are these little absorption lines in galaxies called the H and K lines. These are ionized calcium, which exists in the photospheres of stars like our own. G-class stars, I think K-class stars are cool enough, are warm enough to have the ionized calcium still. F-class, I'm not sure about A-class, but basically stars which are right around our mass or our sun's mass, really. So we get these blue violet lines, these HK lines, which are ionized calcium in the atmosphere, which is absorbing this light from deeper within the star. Now, if the galaxies nearby us, okay, such as the large Magellanic or the small Magellanic Cloud, we would expect that these lines would be right here in the spectrum. But as galaxies move faster and faster away from us, we would see these lines shift further and further away. Now, going back to the example of this galaxy moving at half the speed of light, 1.7 times the wavelength, we can actually do a calculation. The H and K lines are right around 395 nanometers. We multiply that times 1.7, that would shift it to 671 nanometers, and that puts us well within the red. So this galaxy right here, if it were shifted all the way, would be moving away from us at about half the speed of light. And what's important too is not only does the light shift, but the intensity drastically is reduced, not just reduced in terms of, we know that intensity is reduced by 1 over r squared, 1 of the distance squared, but also reduced due to the fact that we're stretching these wave fronts out, and therefore they're delivering less intensity than they would if they were just stationary at that distance. So these galaxies are very, very dim and very, very hard to see. So once again, we can actually do a speed measurement on these galaxies simply by saying, okay, I know where the spectral line is going to be. Where do I see it in the spectrum? These ionized calcium lines were so nice because there were a pair of them. So this fingerprint would be very easy to identify. If it was a single line, you'd be a little bit concerned. Now, maybe am I seeing, another element here? But the sodium D line, the calcium H and K lines, just they're very obvious in terms of showing up like a pair like that. Now, astronomers don't like to talk so much about recessional velocity. They like another number, which is known as Z. It's called the redshift. And 1 plus Z is equal to the ratio of the observer's wavelength divided by what the source wavelength would be. So, it gets rid of this whole idea of, worrying about how fast the object is traveling, and really, how much is this light redshifted? So for instance, a redshift of 0, if Z equals 0, 1 would be equal to the observer wavelength divided by the source wavelength, which means that they're the same and basically the object's not moving. However, as the observer wavelength becomes large compared to the source wavelength, Z is going to become larger and larger. And the larger the Z, the faster it's moving away from us. The faster it's moving away from us, the more distant it is, okay? And also, the closer that object is going to be to the beginning of the universe, okay? So here is looking at what we call high Z objects. These are objects that are really, really highly redshifted. The first one we're going to look at is HD1. It currently holds the official record. I'm going to say official because at the time that I made this recording, I saw it to be the official highest Z. We'll get to another galaxy in a little bit. Probably as this poor video ages, this will not be the case, but this is at a Z of 13.27, okay? That means that if our estimations for the Hubble constant are correct, this represents a galaxy which was giving its light off at 13.46 billion years ago. So the time it gave off its light, it was 13.46 billion light years from Earth. So that light has been traveling 13.46 billion years. Now, the universe has expanded since that time. So this galaxy is probably more like 33 billion light years away from us. But this galaxy formed very, very early on, or was seeing light very, very early on after the universe came into existence. Okay? Very soon after the Big Bang. However, thanks to the James Webb Space Telescope, we have what we think might be a good contender to beat this galaxy. It's given a really obscure name, F200 DB-045. Okay? I don't even know what that catalog number means. Oftentimes they categorize these different objects according to some catalog of objects. Messier created a catalog of comet-like objects. that are very common in astronomy. So we'll use like M, I think M1 is the Crab Nebula. There's another catalog of stars where they'll use HD as a prefix. But all these different catalogs of stars will give these, I think this is probably a catalog number, but we'll give some designation rather than giving it a nice name like, Crab Nebula. So in any case, F200 DB-045, we believe is the highest Z object, highest redshift object at around 20. Now, without going into detail about how they measure redshift on this, it does have to do with spectral analysis, but it really needs a lot of follow-up because they make a lot of assumptions when they measured the redshift for this. But it really tells you why the James Webb Space Telescope operates in the infrared. If this light, maybe started in the visible part of the spectrum, okay, is at such a large redshift number. So if we look at this, and we look at Z is equal to the observer minus, okay, so the light that we're seeing has a wavelength 19 times greater than the original light given off. So even if it started in the ultraviolet, okay, let me give it some pretty high number, like 200 nanometers, which is, it's in the near ultraviolet, but let's say that light started at 200 nanometers. It's now, I got to be careful here that I do this right. It's now at 3.8 microns, which is well beyond the limit of what Hubble would have been able to see. So that's why we're using this the way it was designed. The James Webb Space Telescope is really designed to see, into the infrared, because not only does infrared light penetrate very well through the gas and dust of space, these very, very early objects, which we want to study, we want to know what the universe was like very, very early on. And we're being surprised by it. We're seeing that galaxies formed a lot earlier than we thought. And the James Webb Space Telescope is doing a really nice job of bringing up all kinds of great new questions for astronomers to solve. Okay.